Hi everyone. So today we're going to talk about continuous charge distribution. This topic is an important topic in electricity and magnetism course, and it is also an important subtopic in the electric fields chapter. So let's first talk about what is continuous charge distribution. A continuous charge distribution is not a point charge. So you might have calculated the electric field due to a point charge using this formula, which is electric field equals whatever 4 pi epsilon naught, which is our Coulomb's constant and is represented with a small k to simplify our calculations, times by q, which is our source charge due to which the electric field exists, divided by r square, which is the distance from the source charge to the point, and r unit vector. So, and we have an r unit vector here. R unit vector is the distance from the source to the point. So for example, my source charge lies here, and I'm going to find the electric field due to this source charge at point P. So this is my direction of electric field, and now this distance from the source charge to the point is basically my r, and the direction vector is my r unit vector. Okay, so we calculate the electric field of a point charge using this formula. Now you might have multiple charges, like you can see on the screen. So you might have 4 or 5 different charges, and you want to calculate the electric field at a point P due to all these charges, and for that we use the principle of superposition. The principle of superposition adds up the individual electric fields due to each charge and give you the net electric field at a particular point. So here you can see that the formula is given, which is k, and we have a summation sign. So this is adding up the electric field due to each charge. This is adding up the electric field due to charge 1, 2, 3, 4 and 5, and we have individual charges. So here it's q1, it's q2, divided by and so on, and divided by ri squared, which is the distance from each charge to the point, and divided by the unit vectors. So this is how we calculate the electric field at a point due to multiple discrete charges. But in practical cases, you might have a charged rod, or you might have a charged ring, and these are not discrete charges. They have a continuous distribution of charges across the object. So that's why I'm saying that continuous charge distribution is not a point charge. It is a charge which has a shape, and the charge is continuously distributed throughout the object. Now I have a object on screen. I have a blob of charge, and how am I going to calculate the electric field of this blob of charge? So I could divide the object into smaller charges. So I could say that this point here is my charge dq, and I have several little charges throughout this object. So I am dividing the charge of this object into infinite number of infinitesimally small point charges dq. The sum of the infinite number of electric fields via superposition is going to give me the electric field of this whole uniformly charged object. Let me just tell you what's happening. So I might have the charge here. So this is dq1, dq2, dq3, dq4, dq5 and so on. I might have dq36 here. So I am just dividing this whole blob of charge into small, infinitesimally small charges. Now I want to calculate the electric field at point P. So this is charge 4, so I could have an electric field due to charge 4 here in this direction. So due to dq4, I have an electric field. Wait, I should write it as E4, right? So due to E4, and maybe charge the part of charge 36 is here, so I could have an electric field due to this charge in this direction, which is E36. And now I'm going to add up all of these electric fields, all of this infinite number of electric fields, to get the electric field of this whole charge. And since I have a small charge dq, each will give me a small electric field dE. So how will I get the total charge of this object? So the total charge is my capital Q, and I'm going to sum all of these little q's, which I'm saying delta q. All of these little q's I'm going to add up, and I will get this source charge here. And how will I add them? Since I have infinite numbers of charges, and to find the addition of a continuous source, we take an integral. So I'm going to take the integral over all 3 dimensions over the volume, and I will get my total charge Q here. Okay. Now, let's calculate the electric field at the point P. I have T EP, which is the electric field, which is the small part of electric field, which is equal to K dQ over R square R unit vector. And I'm going to integrate on both sides to get the total electric field of P. And I get this formula, K dQ over R square R unit vector. Okay, before I dive into calculating the electric field due to a continuous charge source, I want to talk about the charge densities. Okay, so we have 3 different charge densities. We could have linear charge density, which is represented by a symbol lambda. Linear charge density is a total charge Q distributed along a line with a length L. If an element of line DL is charged with an element of charge dQ, the linear charge density is defined as lambda equals dQ over dL. So if I have to calculate the linear charge density of this rod here, so this is going to be the total charge divided by the total length. But if I want to find the linear charge density of a small part, so I'm going to take this small length dl and this small charge dq, and I'm going to divide this, and I will get the linear charge density. The other type of charge density we're going to look at is surface charge density. This is represented by a symbol sigma. Surface charge density is when we have a charge Q distributed across an area, and we calculate surface charge density to calculate a charged object of total charge Q distributed on its surface area. Consider an element of surface dA, a small area dA. The total area is capital A and the small area is dA, charged with a small element of charge which is dQ. The surface charge density is then defined as sigma equals dQ over dA. And if I want to find the surface charge density of this whole object, this is going to be my total charge Q divided by the total area A. The dimensions of linear charge density is, so we have the unit of charge as coulombs, we have a unit of length as meters, so the dimensions are going to be coulombs per meter. The dimension of surface charge density is going to be the unit of charge as coulombs, and the area is meter squared, so this is going to be coulomb per meter squared. The total charge on the object is obtained as the integral over the surface of the object. Since I have a continuous distribution across the object, if I want to find the total charge across this object, I'm going to rearrange my formula. So Q equals a sigma A. Since I now have dQ into sigma dA, I'm going to take integral on both sides, and this is going to give me Q into sigma dA. And the limits will be the area. Now the last type of charge density we're going to look at is volume charge density. This is represented by a symbol rho. Consider a charged object of total charge Q and a volume V. So here I have a sphere. The total charge of this sphere is A and it has a volume V. Consider an element of volume dV, a small element of volume dV, charged with an element of charge dQ. The volume charge density rho is defined as dQ over dV. Again, if I want to find the total charge density of this whole sphere, this is going to be total charge divided by the total volume, and the dimensions is now going to be coulombs per meter cube. And then again, if I want to find the total charge, I'm going to take the integral over the volume of this whole object and rho into dV. So my integration variable here is the volume. Okay, so now we know what charge density is. I have a question on the board, so I want you to pause the video now, give it a go, and then we're going to go through the question together. Okay, so welcome back. This question is very easy. Now let's talk about it. I have a few figures, a few objects on my screen, and I have to calculate their charge densities. The objects shown in the figures above are all uniformly charged. Uniformly charged means that the charge is distributed evenly across the object with a total charge Q. Just a second. Okay, with a total charge Q. For each object, express Q in terms of lambda, linear charge density, sigma, surface charge density, or rho, volume charge density, and the geometric vectors L, H, R, R1 and R2 as needed. Okay, so first of all, let's calculate the charge density of this solid cylinder. So I have this solid cylinder with a height H and with radius R, and I need to find the total charge Q. I know the formula that okay, first of all, you need to identify which one second. Okay, yeah, so first of all, you need to identify which charge density relates to these objects. So for this cylinder, is it a one-dimensional object? If it's a one-dimensional object, I will use the charge density which is linear charge density. If it's a two-dimensional object, I will use the charge density which is surface charge density, and if it's a three-dimensional figure, then I will use the charge density which is volume charge density. So I can see that this is a whole three-dimensional figure, so I will use this rho, volume charge density, and I know the formula which is equal to dQ over dV, which I just have done a few minutes ago. Okay, so yeah, so now let's rearrange this. I'm going to integrate on both sides to find my total charge Q. Q equals rho dV. Okay, since I have a cylinder here, what's the formula for calculating the volume of a cylinder? Yes, it's pi r square h, where h is the height and r is the radius. And my integration, okay, since I have dV here, so I'm going to show you a little thing here. So if I integrate this formula over r, so if I differentiate this, so I have dv over dr, I'm going to get 2rh. Okay, so dv over dr, if I differentiate this, I'm going to get pi 2rh. So this is basic calculus here, and if I now rearrange this, I will get pi 2rh dr, and I can put this in my formula. You don't need to do that for this simple question, but I'm just going to tell you about the integration variable in this case, because we know that our volume is not changing. The thing that will change is the radius. So we are going to integrate over the radius, okay? So I will get 2 pi r h dr, and since I know that my volume charge density is the same throughout the object, so I can take this out of the integration. My 2 pi is a constant, my h is a constant, so I will just integrate over dr, and I'm going to put my limits here. So my upper limit is the total radius r, and my lower limit is 0. So what I will get, rho 2 pi h r, since I'm going to integrate this, so this is going to be r square divided by 2 over the limits r and 0. So this is going to give me 2 pi h r square over 2 minus 0 over 2, which is just going to be 0. So this is going to give me pi r rho pi r square h, and this is the total charge of this cylinder. So I did this using this formula just to show you that our integration variable usually in these cases is the radius, but I could just do it directly like this. So I could have q equals rho dv, and if I put my rho out of the integral variable because it's constant, I will get rho v, and I can just simply put my formula. I know my radius, which is capital R, so I can just simply put my formula here, and I will get the total charge Q. Okay, so this was easy. Now let's talk about the other one, which is my thin rod with a length L. So this is part B, a thin rod with a length L. Now this is one dimensional, so I will use linear charge density lambda. I know my total charge is Q, so this is Q over L. So this is going to give me Q equals lambda. And yeah, so since we are dealing with the integration variables, we know that our length can change, so I will use dq over dl. This is the most accurate form of this formula. Okay, so this is going to be dl integral. Again, the limits is going from 0 to l, so I will get lambda l minus 0, which is going to be lambda l. Yeah, pretty easy. Let's talk about the third one. This is cylindrical shell. So this is a bit tricky, not too tricky, just a bit tricky, because we now have a three-dimensional object, but since it's a cylindrical shell, the inner side is empty, so the charge is distributed among the radius r1 till r2, where r1 is lesser than r2. Now a simplified approach is that I will calculate the total charge of the radius r2, and then I will subtract the charge of the radius r1, and in this way I will get my charge which is distributed between r1 and r2. So let's do that. Again, Q equals rho dv, and I will find dv2 and dv1, and then I'm going to subtract them. So Q equals rho v2 dv2 q equals rho dv1. So this is going to be q equals v2, q equals rho v1. And the total charge is going to be, this is sorry q1, this is q2, and total charge is going to be, it's the other way around actually, q2 minus q1, which is going to be rho v2 minus rho v1. I'm going to take the rho out, v2 minus v1. Again, since we are integrating from 0 till r2 and from 0 till r1, so this is going to give me pi r2 squared h minus pi r1 squared h, and I'm going to pull out my pi and h because this is same. So this I will end up with r2 squared and r1 squared. So this is the total charge of a cylindrical shell. Now the third case here is of a solid sphere with radius r. I think it's the D part, yeah. So solid sphere with radius r. Okay, have a go at this one. So since again it's a solid sphere, so we have a volume. Okay, so this is going to be q equals rho dv. dv is again going to be, since I'm integrating of the whole object, so this is just going to give me my v. My v, the volume of the sphere is going to be equal to 4 by 3 pi r cubed. So this is going to be rho 4 by 3 pi r cubed, and this is the total charge of this sphere. And finally we have a thin disk with a radius capital R. Have a go at this one. So since now we have a thin disk with an area with a radius r, so we are dealing with an area we are dealing with a two-dimensional object, so we are dealing with an area, and so the charge density we're going to use here is sigma. Sigma is again equal to dq over dA, and q is then equal to sigma dA, where sigma is, when we integrate it, this is going to be sigma a, and the a in this case, since this is a charged disk, is going to be pi, and the radius is capital R, so going to be sigma pi r square, and this is my charge for this object. So this was our first task on calculating the total charge using the charge densities, and then we're going to build on this, and then we will talk about calculating the electric field due to a charged rod, due to a charged ring, due to a charged disk, and due to a charged cylinder, and so on. Now let's do the charge density task 2. Here is the task. Pause the video and have a go at this task. Now, okay, well done. Now let's have a go at it together. So part A, a charge is uniformly distributed along a thin rod of length L. So the length of this rod is L. The charge of small element of rod of length delta x is given by, so since we need to find the charge of small element, I need to find delta q. Okay, very simple. We have the charge density we are using here, which is lambda. Lambda is our linear charge density, which is equal to delta q over delta L. And if I talk about this whole rod, my lambda is equal to q over L. So I'm going to put these equal to one another, delta L Q over L. And if I rearrange this, I will get my delta Q as Q over L delta L. Very simple. The charge Q is uniformly distributed throughout a rectangle of length A and height h. Here, the charge of a small element of the rectangle delta Q of length delta x and height delta y is given by, so we need to find the charge, the small element of charge delta Q. Again, this is a rectangle. We have an area here. It's a two-dimensional object, so we have an area here, and we're going to deal with sigma. Sigma equals Q over A. For this whole object, A is equal to width, since it's a rectangle, so this is going to be height into width, so this is going to be AB. Sigma is going to be Q over AB. And if I deal with this a small particle delta Q, so this is going to be delta Q over delta A. Now, how will I find delta A? Delta A is equal to this small element delta X into delta Y. This is my width and this is my height. And I'm going to put this into the formula delta Q over delta X delta Y. And then again, I'm going to equate equation 1 and equation 2. And I'm going to get my small element delta Q as this. So I now have Q over AB equals delta Q over delta X delta Y, and again delta Q is equal to Q over AB into delta X delta Y. Perfect. Now let's talk about the final part. A charge Q is uniformly distributed throughout a disk of radius r. Consider the charge element to be the ring of inner radius small r and a very small thickness delta r. The charge of the ring is given by, so we have a thin disk here, and we need to find this delta Q of this small ring with the inner radius r and the thickness delta r. Okay, so again we have, since we have an area here, so this is going to be Q over A. It is a disk, so my area is going to be pi r square. Now if I talk about the small element dq, this is going to be delta q over delta a delta q. Now how will I find my delta a? Delta a is basically my, so since my a is equal to pi r square, my delta a over delta r, which is just, I'm just going to integrate it, differentiate it, and I will get 2 pi r, and if I now take this delta r on the other side, I will get 2 pi r delta r, and I'm going to just put this here, 2 pi r, sorry, the formula is small r, not the big R here. Big R is after putting the limits, okay? So 2 pi r delta r, and I'm going to put these equal to one another since both of them are equal to sigma. 2 pi r delta r equals q over pi r squared. I'm just going to pi r squared, so this is going to be q over pi r squared times by 2 pi r delta r. Cancel this pi, and we are going to get delta q equals q 2r delta r over r squared. So this was all for the charge density. In the next videos we will cover how to find the electric field due to a uniformly charged rod, due to a ring of charge, due to a cylinder, due to a disk. So that was all. Just put your feedback in the comments, and bye bye.